Section 2.5, we're going to be looking at chain rule and parametric equations. Specifically, we're going to start with just some higher order derivatives involving the chain rule. And so I hope you've been practicing in previous sections and you feel confident in your other rules because you're going to see us using them repeatedly. So what I want to do in the first example is I want to find the first derivative. And then once we have found that and simplify it up, I want to see what it looks like for us to find a higher order derivative, such as maybe the second derivative. And so what I want to do is I'm going to have to execute product rule and also my rule about natural logs. So I'm going to say f prime of x is equal to derivative of the first, which is 18x, times the second, which is ln 7x, plus the first, 9x squared, times the derivative of the second. Remember, natural logs, you put your 7x on bottom and you put its derivative, which is just 7 on top. This is my raw derivative, so I'm going to clean it up a little bit. So this would give me 18x ln 7x plus, let's see, our 7s would cancel, our x would cancel, leaving us with a 9x. And so this would be my first derivative. If it asked us for our second derivative, the only way we can get to a second derivative is we first find the first derivative. There is not a way for us to jump directly to the second derivative. We have to take these steps in between. And also why we emphasize cleaning up and simplifying your answers so that you have a much better piece to work with when we move to second derivative. Now for second derivative, I am going to clean it up a little bit more in the fact of, do you notice that we actually have a common factor between those two terms? These both have a 9x in common. So I'm going to factor that out. That would give me a 2 ln of 7x plus 1. And so what I'm going to do again is I am going to take the derivative of this simplified function. So I've got a 9x and I've got this term here. So the derivative of 9x is 9 times everything else plus 9x times the derivative of the other one. Okay, well, let's see. The derivative of 2 ln 7x. So I'm going to draw my fraction bar. 2 is going to go along for the ride. I am natural logging 7x and its derivative is 7 plus the derivative of 1, which is just 0. So now if I clean this up, this gives me 9 times 2 ln 7x plus 1 plus this cleanup. Let's see, the 7s are going to cancel, the x's are going to cancel, and I have an 18. And so I'm going to go ahead and distribute that out. So it gives me 18 ln 7x plus 9 plus 18. I'm going to combine like terms. 18 ln 7x plus 27. And if I wanted to, I could furthermore maybe bring the 18 up just to apply my log rules. And so I end up with ln of 7x to the 18th plus 27. So I wanted to review some of our rules and properties that we've already been doing in other sections before we move into this idea of a parametric equation, because we're going to be applying our derivatives and then we're also going to be looking at some higher orders of them. So to give us an idea of parametric equations, I think Sal says it best. So let's jump over to him and see what he has to say about parametric equations.
Let's say I have a cliff. Let's make this cliff, I don't know, let's say it's 50 meters high. 50 meters. And on this cliff, I have a car. And this car is not just sitting on the cliff, it's driving off of it. It's a very dramatic problem. So let's see, I have this car here, and it's driving off of this cliff at 5 meters per second. 5 meters per second. And I want to know, what is the path of this car as it falls off of the cliff? So let's set up a little coordinate axes here. Let's say that I get my y-axis. So let's say that this is the y-axis right there. And then this will be my x-axis. X-axis. So this is y. This is x. Let's say that this is the point. Well, we know this is a 50-meter high cliff. Maybe y equals 0 is sea level. So this would be 50 right here. And let's say that this point right here on the cliff, that's at x is equal to 10. So this point right here is a point 10, comma 50. And let's say that the car is right at this point, right about to drive off the cliff at time is equal to 0. So this is at time equal to 0. Time equal to 0. So t for time. Time is equal to 0. So my question is, what happens to this car as it drives off the cliff? So this is a bit of a physics problem, and I won't go deep into the physics, and I won't prove some of the equations, and I encourage you to watch the kinematics videos, the projectile motion videos, if you want to know where the equations come from. But the point here is just to get the equations and see what the graph looks like. So if I wanted to know x as a function of time, x as a function of time, let me suitably vibrant color. So x as a function of time is going to be what? Well, we're going to assume that we're on a planet that has no air. We're in a vacuum. So if we start off in the x direction at 5 meters per second to the right, we won't be decelerated by air or friction or anything else. Newton's laws of motion: an object in motion stays in motion unless it's affected by a net force, and there won't be any net force in the x direction. So it's just going to keep moving to the right at 5 meters per second, and position or distance is just equal to velocity times time. Our velocity is 5 times time. And of course, it didn't start at x is equal to 0, right? This is at time is equal to 0. So it started at x is equal to 10. So you want to know it's kind of x of 0, or where it started off, so plus 10. And this should be a little intuitive for you, right? At time is equal to 0, this term cancels out. We're at x is equal to 10. That makes sense. At time is equal to 1, we should be we'll be 5 meters further out, so on and so forth. Fair enough. That's x as a function of the parameter time. As you probably realize that this is a video on parametric equations, not physics, so it's nice to early on say the word parameter. 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 And time tends to be the parameter when people talk about parametric equations, although it could be anything. It could be radius or angle or who knows what else. So let's figure out what y is as a function of time. So y as a function of time is going to be equal to the initial y position, or y of 0, which is 50. We're 50 meters up in the air. 50 meters up in the air, plus our initial velocity in the y direction, and we don't actually have any initial velocity in the y direction. The car isn't jumping or isn't diving. It's just moving horizontally to the right, and the cliff is supporting it. So it has no y velocity. But if you were curious, it would be the y velocity times time. But since there's no y velocity times time, at least initially, I'll put nothing there. Plus the acceleration of gravity times time squared over 2. We want to figure out the sign. And just so you know, I mean, it's nice to touch on the physics a little bit, just so you know where these formulas come from, and you know the motivation behind why you would even use a parametric equation. Gravity goes downwards in this example, and downwards in this example is in the minus y direction, where y is decreasing. And the real, and it's not exact, but gravity is normally 9.8 meters per second squared in most textbooks. But for the sake of simplifying this, we'll say that it's approximately 10 meters per second squared. That's how fast everything will be accelerated downward on this planet. Since it has no air, let's assume it's a planet with a little bit more mass than Earth. And since it's going downwards, its direction is negative. So in our formula up here, it's our initial position. We had no velocity times time, so I won't put that there. Minus 10 meters per second squared times t squared over 2. And you can watch the projectile motion videos to figure out how I got these formulas right there, but that's not the point of this. The point of this is to graph what happens to the cars and learn a little bit about parametric equations. So what is the path of this car as it falls off the cliff? Let's make a table here. Let's make a table, and I'll do so x and y are a function of this third parameter, t. So we're going to set t at different values, and we're going to figure out what x and y are equal to. And I'm just going to arbitrarily pick some t's. T is equal to 0, t is equal to 1, 2, and 3. At time is equal to 0, what is x? X of 0, if this is 0, x is equal to 10 meters. At time is equal to 1, what is x? So this is x of 1, right? If I wanted to write that notation. So 5 times 1 is 5 plus 10 is 15. X of 2, 5 times 2 plus 10, that's 20. And it makes sense. Every second we're getting 5 meters more to the right, or x is increasing by 5 meters. So when t is equal to 3, 15 plus 10 is 25. Easy enough. The y is a little bit more complicated. And just to simplify this is the same thing as 5, right? 10 divided by 2. So 50 minus 5t squared. So time is equal to 0. This term cancels out. We just have 50 meters up in the air. At time is equal to 1. 1 squared is 1 times 5 is 5. 50 minus 5 is 40 or 45 meters in the air. Is that right? Right. Yeah. Time 1, 50, right? And then at time is equal to 2. 2 squared is 4. 4 times 5 is 20. 50 minus 20 is 30. And then finally, at time is equal to 3. And I just say finally because that's the last number we picked. Time is equal to 3. 3 squared is 9. 9 times 5 is 45. 50 minus 45 is 5. So let's plot these points. So time is equal to 0. That's what we got right there. At time is equal to 1, where x is equal to 15. That's roughly, see, this is 5, 10, 15. Let me do all of them. 15, 20, 25. And then the y-axis, let me label that while we're at it. So this is roughly 10, 20, 30, 40, 50. So time is equal to 0, we're at 1050. That's that point right there. At time is equal to 1, we're at 1545. So x is 15, y is 45, which is right about there. So this is t is equal to 1. At time is equal to 2, we're at the coordinate 20, 30. So 20 and 30, it's right about there. So this is at time is equal to 2. And then at time is equal to 3, we're at 25, 5. So we're right there, 25, 5. Time is equal to 3. And if we kept going on, at some point we're going to hit the ground. And you can figure out, actually, set this equal to 0 and you figure out the exact time you hit the ground. Actually, let's do that. If this is equal to 0, 50, you get t is equal to the square root of 10, which is a little over 3 seconds, which makes sense, right? A little over 3 seconds, we're going to be hitting the ground. But anyway, what's the path of this car? Well, it's going to look something like this. It's going to look like this. Ooh, it starts getting accelerated downwards, and then plunk, it hits the ground at 3 point something seconds. Now, what was interesting here is that by setting the parameter, not only did we get the curve, right? We got this curve, which is kind of half of a parabola, half of a downward shaping parabola, and we can actually eliminate the t and just get the equation for that parabola, and we'll do that in future videos. But what was interesting, by making it a parametric equation, we know the direction of the car. If you just saw this graph without the car and everything else I drew, you would know which way the car is falling. But now we know that as t is increasing, we're going in that direction. So we can draw some arrows here. So because it's a parametric equation, we can draw some arrows. And then the most important thing is we know exactly where the car is at any time t. You can substitute t is equal to 1.25 seconds, and you know exactly where the car is. So you can plot these points, and you can kind of get a sense that as time goes on, we're getting accelerated downwards. And that's why for every second further, especially the y distance gets further and further apart. Anyway, I just wanted to give you this example. Although this was a good physics problem, the intention wasn't to teach you physics. The intention is to give you the motivation behind why parametric equations even exist. Parametric equations. These two things are parametric equations. We defined x and y as a function of a third parameter t, instead of defining y in terms of x or x in terms of y like we've done every other time since then. And this is super useful. I mean, you can imagine when you have really hard physics problems where you want to figure out the three-dimensional position of something, then you'll have x as a function of t, y as a function of t, z as a function of t. All sorts of interesting problems come out of using parametric equations, not just in physics. But anyway, I thought a good place to start is the motivation, because the first time I learned parametric equations, I was like, why mess up my nice and simple world of x's and y's while introducing a third parameter t. This is why, because you can figure out the path of things. You can figure out the direction of something as it moves along a curve, and you can figure out its exact position at any, in this case, time.
Thank you, Sal. I think that point and that problem really helped us to see of this switch and the shift to parametric equations. And so what I want to do is let's go into our own example. Let's switch on over to our own set of parametric equations, and let's look at what's going on with this. So say we have, let x of t be equal to t cubed minus 4t squared plus t, and let's let y of t equal t squared minus 6 of t plus 3. Going back to that explanation of where do these equations come from, why are we setting these up, and that goes into the previous part that Sal just explained for us. And so what I want to do is I want to take this a step further, and let's look at some derivatives of these functions that are created, and then also let's look at some spaces in time and what those values look like. So if I want to, in this next step, find the slope of a tangent line, I am trying to get to the point in all of this process of finding dy dx to find that slope at a tangent line. But in order for me to get to the dy dx, I'm going to have to find what dy dt is, and then I'm also going to have to find what dx dt is, and then divide those two to get that dy dx that we've been working with throughout this chapter. And so I'm going to take each individual equation and find their derivatives. First, I'm going to start with dx dt. So this is going to be equal to just taking the derivative of this with respect to t. So that means all of our rules will apply. We're just using t instead of the x like our other problems. So this would be 3t squared minus 8t plus 1. I also want to find dy dt. So I'm going to take the derivative of this function with respect to t. So that would be 2t minus 6 plus 3. Now, if I want to pause there with each of those functions and just look at what is going on in relation to those functions in relation to a space and time, I could look at them in regards to t equal to 1. What's happening at 1 second? And so I could take each of those functions and just plug in 1. So in this first one, I could plug in 1, do some simple arithmetic, and I get it to be a value of -4. Then I could take the 1, I could plug it into dy dt, and again, excuse me, I messed up that derivative. The derivative of 3 is just 0, so I don't need that. Sorry for that mistake. I plug in 1 into this one, and you can see I just get -4 on it as well. So I can approach the derivatives of these individual functions, but if my end game is to figure out what dy dx is, then we need to jump down to that. But now we have our pieces that we need, and we've seen how we can work with them. So if I'm looking at the slope of a tangent line that from those parametric equations is, I'm going to use my information from above. And we just said that this is equal to dy dt over dx dt. And so this is going to be equal to my equation for dy dt, which I just corrected, which is 2t minus 6, all over my equation for dx dt, which is 3t squared minus 8t plus 1. Now I can't simplify this up any, so I'm just going to leave it as is. And so this is the slope for any given point of the situation similar to the one we just saw in the example as it's moving along or falling off a cliff, etc. So if I want to find the slope of the curve that is created, say of something falling off the cliff there, then we can take our now dy dx and we can look at the value of 1 second, say, okay, what does that look like? Well, we know that plugging in 1 to the top we just saw was -4. Plugging in -4 into the, 1 into the bottom gives us -4 as well. And divided, that gives us 1. So this right here is the slope at 1 second of the parametric equations that are being created, such as maybe something falling off the cliff or etc. So I know that was a lot of information for parametric equations, but I felt like I couldn't really jump into this example and show you why I was working with t's and creating dy dx without pausing and explaining what's going on with parametric equations.